Hello, my name is Boris Polyakov. I am a senior researcher at Thin Film Laboratory, Institute of Solid State Physics. Today I will tell you about thermochromic nanomaterials for additive printing technologies. What are smart windows? Smart windows are able to change their transparency depending on such parameters as temperature or light intensity. Why smart windows can help us to make rooms and indoor space more comfortable for being and living. Smart windows are able to control heat and light flux through windows. We can distinguish two main types of smart windows. That's active windows which needs power supply and control. For example, electrochromic windows and passive or self-switching windows which don't need external power supply and additional control. They react to either illumination or temperature. Vanadium dioxide usually used for inorganic thermochromic coating for smart windows. Vanadium dioxide have phase transition at temperature around 68 degrees Celsius. It switches from semiconducting phase to metallic phase. During semiconducting phase, vanadium dioxide coating is transparent for infrared light. If temperature rises, it switches itself to metallic state and able to reflect light. At cartoon, you can see illustration of smart windows which reflect heat and make life of indoor people more happy and comfortable, in contrast to normal window. On this slide you can see spectrum of sun. We can see only narrow part of solar spectrum which is visible. We are unable to see ultraviolet light and infrared light, but we can feel infrared light. For example, if you are standing in front of open fire, you can feel heat which is transduced from fire by radiation, that is infrared radiation. On graph I put on graph of solar spectrum I put also transmission spectrum of vanadium dioxide coating in semiconducting or inactive state and metallic or active state. Actually, this graph demonstrates modulation of infrared radiation. There are a lot of other inorganic thermochromic materials. You can see a lot of them on this slide. But unfortunately, only one or vanadium dioxide have phase transition which is relatively close to room temperature, that is 68 degrees Celsius, and for real application in reality it is necessary to shift it closer to room temperature, and in next slides I will mention methods which we can use to achieve that. There are several approaches how we can fabricate thermochromic coating on glass surface. First of all, that's physical vapor deposition that includes magnetron sputtering and pulsed laser deposition, that's chemical vapor deposition and atomic layer deposition, and nanoparticle based coatings. The last one, nanoparticle based coating and physical vapor depositions are methods which are scalable. So on this slide in more details you can see all these methods, and if you are interested you can follow the given link to take a look. That chemical approach which use nanoparticles based inks, that's first of all roller coater, spray coater and inkjet printer. For today, roller coating is the most simple and the most popular method for producing thermochromic coatings. But in future, I think inkjet printing may become quite a powerful method for producing smart windows. Now, in more details about synthesis of vanadium dioxide nanoparticles. Probably the most popular one is hydrothermal synthesis method. So we mix precursors, prepare a solution and load it into autoclave, which we place inside oven for a certain time and temperature. After synthesis, it is necessary to calcinate obtained nanomaterials. After that we dry it and obtain vanadium dioxide nanomaterials. Next method, hot injection method, allows to produce very fine vanadium dioxide nanoparticles. But after synthesis, these nanoparticles have crystalline structure which have no thermochromic properties. To modify crystalline structure of nanoparticles, thermal sintering can be used. These tiny nanoparticles are very good for producing of vanadium dioxide based inks for inkjet printing. Next method is pyrolysis. After preparation of liquid precursor solution, it is spray coated onto hot substrate. That is possible to achieve very good physical properties of vanadium dioxide thin films. Quite close method is Zoll-Gel method. So first of all, precursors are solution prepared from vanadium dioxide precursors. It is aged for a certain time at a certain temperature, and after that sample is coated with vanadium dioxide precursor and dried. To achieve high thermochromic performance, it is necessary to process films. In this case, laser annealing is used. And combined synthesis method. First of all, nanomaterials are synthesized using hydrothermal method. After that, nanomaterials are calcinated in oven in controlled atmosphere. And after that, ball milling in solution in presence of surfactants is used to achieve a proper size of vanadium dioxide nanoparticles. Usually, After deposition of vanadium dioxide, annealing is needed to improve thermochromic performance. That may be thermal annealing or light annealing. In both cases, at proper parameters, nice thermochromic performance of vanadium dioxide thin films can be achieved. There are three main parameters which can be used to characterize and compare thermochromic vanadium dioxide coatings. First of all, that is luminous transmission. That means how transparent the film is. The higher transparency, the better. Second one is solar modulation, which show difference between active and inactive state, or ability to block light. And last is phase transition temperature. The closer it is to room temperature, the better. If you take a look at this table, in which a lot of elements used for doping are listed, we can find out that tungsten doping is the best. Unfortunately, as a drawback of elemental doping, decrease of solar modulation usually occurs. In case of nanoparticles, to improve transparency and to increase environmental stability, core shell approach is used. Vanadium dioxide core can be coated with silicon oxide, zinc oxide, titanium oxide, and aluminum oxide. One more method to improve thermochromic parameters is multi-layers or anti-reflecting coatings. What is nice about this method, it helps not only to improve transparency, but also to improve solar modulation. After vanadium dioxide coating deposited on substrate, we can use several methods to characterize its structure and morphology. That is X-ray diffraction, transmission electron microscopy, and scanning electron microscopy equipped with energy dispersive X-ray spectroscopy, or ADX, and X-ray photo electron spectroscopy. I use this article as a demonstration of application of these methods. X-ray diffraction can be used to see how crystalline vanadium dioxide is and to exclude presence of our oxides like vanadium 2O5. ADX can be used to measure amount of dopants, tungsten in this case. XPS can be used to probe valence state of vanadium. Scanning and transmission electron microscopy allows to see morphology of obtained nanomaterials as well as their crystalline structure. For advanced characterization, synchrotron radiation can be used. Synchrotron is a huge machine which accelerates electrons, and if electrons are deflected, they emit quite intense beam of X-rays. One of the method is EXAFS. or extended X-ray absorption fine structure. These methods allows to prove local atomic surrounding of atoms. As example, I put here rhenium doped vanadium dioxide thin films studied by EXAFS spectroscopy. What we can see and what we can conclude. Actually, EXAFS is a rare method which allows to study local surrounding of doping elements like rhenium in this case. We analyzed the spectrum of rhenium which is in matrix of crystalline vanadium dioxide. And spectrum coincided with orthorhombic rhenium O2. And that means that rhenium indeed substituted vanadium and effectively works as a dopant. Spectroscopic ellipsometer with heating table and UV-VIS-NIR spectrophotometer with sample heating can be used to characterize thermochromic thin films. Spectroscopic ellipsometer give us a possibility to see how doping of rhenium in this case shifts phase transition temperature. So on these graphs you can see that with increasing amount of rhenium, phase transition shifts to lower temperatures. To see how effectively works vanadium dioxide doped with rhenium, we also studied transmission spectra of vanadium dioxide coating at room temperature at elevated temperature, 100 degrees in this case. And you can see that with increasing amount of rhenium in film, thermochromic performance decreases. In these last two slides, I will advertise our institute a little bit. Institute of Solid State Physics have extended infrastructure for research of new materials, including nanomaterials. Exactly this year we started ERDF project about smart windows with acronym SWITCH, or smart windows for mixed thermochromic photochromic coating and enhanced anti-reflective functionality. This project will be realized in collaboration with Grow Glass Factory, which is a leader of manufacturing of anti-reflective glasses for museums. Thank you for your attention.